All right, thank you for the introduction, ladies and gentlemen. We all know about the advantages of additive manufacturing, particularly when it comes to processing parts and components with complex shapes and geometries. Unfortunately, we also know about some of the disadvantages, and that many additive manufactured AM materials exhibit defects such as pores and micro cracks. And when it comes to structure property relationships, we need to, of course, pay attention to microstructure that can be quite different depending on whether we look into the build direction or perpendicular to the build direction. And then there is also additionally this mesostructure that we do not really have available in conventionally processed materials, that adds an additional length scales of structure that we need to take into consideration when we assess the mechanical performance of these materials. And these are all factors that we need to understand and control in order to understand and tailor the mechanical properties of these materials. In order to do this, we have looked at two different types of materials. The first one is this LPBF process, the aluminum silicon 10 magnesium alloy. To get pores and microcracks under control, we use this Gaussian process regression-based machine learning approach, where we essentially printed materials with different combinations of particularly laser power and scan speed that were varied over a wide range, while keeping hedge spacing and layer thickness together. Then from the printed materials, we essentially measure the relative density. And when we plot now relative density in this graph here, where we have scan speed over laser power, we can see that we have a very wide range of processing parameters available that we can utilize to make material with high relative density. From this processing parameter window, we have then picked 5 different conditions where we have different laser energy, so energy density that varied over a specific range. And if we now look at mechanical properties, we can see that with changing energy density, we get quite a bit of variation in our mechanical performance. To dig a little bit deeper, we have then printed additional batches, 4 additional batches of material that all had the same energy density, in this case of about 50 joule per cubic millimeter. In this case, we started varying now the individual processing parameters, hedge spacing between 100 and 190, layer thickness between 30 and 60, and scan strategy, as you can see here, between 67 degrees for the first 3 batches and 90 for the 4th batch. If we look a little bit closer now at the microstructure, first of all, at these EBSD scans, we can see for the very left part here with the EBSD scans, they all look a little bit messy, but the one on the left was printed with 60 layer thickness compared to 30 for all others. There's already, we can see a difference that we have more epitaxial grain growth and larger grains. Other than that, there is not so much to see in these EBSD scans. When we zoom in a little bit closer into the microstructure, we can see that inside the melt pools, we have this fine cell structure that is due to the higher temperature and the fast cooling rate. When we go from the interior of the melt pool towards the melt pool boundaries, we get a coarser cell structure, which is caused by the smaller temperature gradient. And then we have this heat affected zone, where essentially the previous deposited layer, the structure, breaks down because we bring a subsequent layer on top of this. If we now look at the first assessment of mechanical properties, we can see here with our nano indentation measurements that we get always for all 4 batches at the melt pool boundary a lower indentation hardness compared to melt pool interior, but also that the material that was printed with lower hedge spacing has overall a higher hardness as compared to the material with the higher hedge spacing. This also translates then into our tensile stress strain behavior. Again, material with smaller hedge spacing shows overall higher strength, higher yield strength, tensile strength, comparable ductility about as compared to the 190 hedge spacing. So hedge spacing significantly influences the strength of the material. And this is caused just because we have with lower hedge spacing, we decrease the cell size, and therefore the strength goes in a whole patch type relation out. The same for layer thickness. Layer thickness, as we said, influences the grains that grow here. And these grains, layer thickness, increasing layer thickness, grain size goes up, therefore strength goes down. What matters obviously also is in what direction we test these materials. Horizontal direction shows overall we see more shear failure due to lack of triaxiality, despite using quite large samples. Vertical samples compared to that, however, show some type of cup and cone failure, which is primarily caused by failure along these melt pool boundaries. And in these samples, we end up with significantly less ductility. After all this tests, we have then, of course, also looked at fracture toughness in these materials. What we find overall is that samples that were tested with a crack propagating parallel to the build direction as compared to the other orientation, perpendicular orientation or the orthogonal orientation to this, we can see that they have an overall way more pronounced R-curve behavior as compared to the other orientation for all different batches of material. Once we start playing with layer thickness and hedge spacing, we do not really see that they impact our R-curve behavior significantly as compared to what they do to strength. However, in this case, it's the scan strategy. Once we start playing between 67 and 90 degrees, now this impacts our fracture resistance significantly. All these different batches, however, have a significantly better crack resistance curve behavior than conventionally processed material that in that case was cast and T6 heat treated. There's a fracture toughness of about 19 MPa/m, whereas most of these other ones are between 20 and 30, which is quite a dramatic increase. Where does this difference between these two orientations now come from? For that, we looked at the samples after testing. We basically sliced our samples in half, then looked at the crack path. And what we find for the crack propagating parallel to the build direction is that we see a lot of these crack deflections out of the mode 1 plane along these melt pool boundaries. And this requires more energy. Obviously, in some cases, it goes throughout the melt pools. And this leads to the much more pronounced R-curve behavior due to these large deflections that lead to large CTODs as compared to the other orientation, where lots of these melt pool boundaries are available and the crack can just propagate along these melt pool boundaries, smaller CTODs, and therefore overall lower crack resistance curve behavior. And all these mechanisms are overall somewhat more pronounced and effective than what we see in conventionally processed material, where we just get basically crack bridging for the individual silicon needles. So now that we've seen that melt pool boundaries obviously play a significant role in these aluminum silicon 10 magnesium alloys, we were wondering what happens in materials where we do not have such pronounced melt pool boundary structure. In this case, we looked at this 18 nickel 300 Mar-aging steel. This material is known to have a very good combination of strength and fracture toughness. It has been tested before in the conventional processed material as well as in additive manufactured condition. And there is very little to no reported anisotropy in the properties, which is primarily caused because these melt pool boundaries are significantly stronger. They are also they are much sharper, and there is just not the structure that we have in aluminum silicon alloys. So we were wondering, do they play a role at all, or why would we actually use this material? Why would we 3D print this material? To sort this out, we focused a little bit on the heat treatment that we use, that we have to do with these materials. Again, it's normally reported with 70 to 75 MPa/m, which is the same as for conventionally processed materials. So we were then going into how can we modify this material to get more out of it. In this case, we used only one batch with these specific processing parameters. This material after processing has about 2% retained austenite. And then we were essentially going to 3 different heat treatments. First, we directly age the material. In this case, we retain the structure. We retain the melt pool boundaries. We have the cell structure. We increase the retained austenite a little bit, and then we obviously get also, due to the aging effect, these precipitates. Then, in the second batch, we essentially solution treated the material, went up to 1000 C for an hour, then we quenched, and then we did the aging. In this case, we dissolved the melt pool structure. We completely eradicated. In this case, all we have is, after the aging, is precipitates. The third one, we thermally cycled the material close to the austenite finish temperature in 2 of such cyclings, and then we did the direct aging. In this case, we keep the structure, but we increase the retained austenite fraction to about 10 to 12%. Now, how does this impact mechanical performance? Specifically, we looked first on tensile stress strain behavior. Overall, we do not really see a lot of anisotropy in our mechanical performance. For the directly aged material, we measure tensile strength of about 1.2, 1.3 GPa with a fracture toughness of 150 MPa/m. This is a very good material. But this is not really how the material is used. There are cheaper materials that can do similarly well. But once we now start looking at the material that was directly aged, we increase the strength to 2 GPa, reduce ductility, and fracture toughness, however, drops to what has been reported before, about 60 to 65 MPa root meter. Once we eradicate the structure of the melt pool structure from the 3D printing process, what happens is that we also get rid of the remaining ductility, that the fracture toughness drops further. And now if we compare to that now, this is not what we want, the direction what we want to go. If we compare, however, the thermally cycled material, we lose a little bit in strength, about 10% reduction in strength, gain post-necking stability and increase the ductility of the material, but at the same time, the fracture toughness now increases to about 100 MPa root meter. And this combination of strength and fracture toughness is something that we cannot really get from the conventionally processed material. So what's causing now this significant increase in fracture resistance that we see for this material after this thermal cycling? For that, we again looked in the interior of the sample at the vicinity of the crack. And what we find we have to remember is that we have overall 10 to 12% retained austenite in this material. Once we get closer to the crack flanks and the path of the propagated crack, we see that there is not a lot of retained austenite. So we get transformation of the retained austenite back into martensite. This is known as transformation-induced plasticity, and we think that this is the main reason why we get such an increase in fracture toughness for this material. Also, for this material that is now retains the mesostructure and that has these microstructural features that we can only get in additive manufactured materials. With that, I should probably summarize my talk. I hope I was able to show that both the micro and especially the mesostructure in these materials is quite important. This mesostructure, obviously, we can only have in these AM materials. They add a structural layer that gives us the ability to play with the properties of the materials and enables mechanisms at length scales that impact both strength and fracture toughness in different ways, but in many ways often positively. Thank you for your attention.